All right. So I tried to look at all the responses. And it looked like a lot of them, kind of what we want to focus on today is do a little bit of contingency table stuff, some of the probability rules, probably a Bayes theorem example. And then if we can do some binomial Poisson at the end, kind of give you some examples of some questions you could see there. Okay. So I'll kind of start out, I might create some questions that weren't on these practice exams. Unless there's like very specific problems that you guys had questions on either one of these practice exams, we could start there. No specific problems here. All right. So I have kind of this set up. We'll use this contingency table. So a real easy one, hopefully, if I ask you to do something like this in the exam, would be to find some value I left off this table. So if we remember, right, how did I say that we could calculate the totals using a contingency table? Yeah, all right, we can just add across the rows or down the columns. So here, I'm adding across the rows, 0.15 plus x is equal to 0.55. And it's just a little bit of algebra, kind of solve for what we don't know. Hopefully that one shouldn't be too bad. Okay. Now I could leave off like one of the totals. So like, let's say I left off this one. Well, then, you can add down the columns, 0.15 plus 0.35 should give you that 0.5. Okay. So hopefully, if you see a problem like that, it should be easy points on the exam there. Okay. Now, it might not be as easy. And I think I have these in a different order on this practice exam, so I'm going to skip around a little bit. Another really easy one, and maybe I flip the order here because I don't know, this one's a little bit harder. Once I get to 7, here I have my events were whether or not someone was a Republican or not, and then I had whether or not they were in favor of marijuana legalization or not. Okay. So here, I want to know what's the probability that an individual is not Republican. Right. So here I'm thinking about being Republican as event R. So not being a Republican would be R complement. Now up in the table, you don't have to write this out in notation if you don't want to, but you can think about it as, yes, they're Republican. This is my event R. No, they're not R complement. Right? You just simply want to write something like R equal yes or R equal no. That would be fine as well. In fact, here it's not yes, right? It's R equal to no. Okay. And then the second part was and. So anytime we see this word and, right, we're looking at the intersection, right? If we had this terminology of or, then we're thinking about the union of two events. So I have and they do not want marijuana legalized. I think I said in the problem, you kind of notate that with LM. Once again, if you wanted to, you could kind of say like legal is equal to no, right? Or they don't want marijuana legalized, LM complement. So it doesn't really matter, like, I don't care how you're writing this, right? Now, when it comes to me asking you about mutually exclusive events and independence, I'll use the notation of whatever the events, however I labeled them here, right? Kind of, whoops. I hate scrolling on this thing. Right? R and LM are going to be kind of our events. But when you're writing this out for yourself, if it's easier for you to kind of write out that way, that's fine. Yeah. 0. Yeah. Well, the short answer questions, I would suggest showing as much work as you possibly can. When it comes to the multiple choice, it's graded for just whether or not it's correct. Right? So there's no partial credit on the multiple choice questions. Short answer questions will be multiple choice. So right now, I pretty much got it finalized and printed today. I think I'm happy with the way it looks. You should have 17, 18 multiple choice questions. And then kind of 2 short answers. Maybe they have a couple parts. But yeah, about 20 questions kind of total there. Any other questions? And question was asked earlier. I will, right, in your exam, you'll have a formula sheet, so you don't have to worry about printing those out. I'll print out the exact one that's up there on Canvas. You'll kind of have that to work through. I'll even pull it up here in a little bit and we'll kind of take a look at it. But for now, we're going to hopefully going through some easy ones and then kind of get to some harder stuff. So if I want the probability of intersections, this should be another really easy problem, right? Because if I want intersections, what do I simply have to do? Yeah, I just go to one of these top 4 left cells and I find where does, my 2 events kind of intersect, I guess, if you want to think it that way. So here, if someone is not Republican and does not want marijuana legalized, that probability of the intersection of those 2 events would be 0.1. It's as simple as looking it up on the table. Okay. Now, it might be a little bit, yeah.
Will we have to make the contingency table like how?
Nope, it'll be given to you just like in this practice exam. These practice exams are very, very good representations of the types of questions you'll see. Okay, so anything you're asked to do on these practice exams, you should know how to do it on the exam. There might be a couple things thrown in there that aren't one of the questions on here, but it's not going to be like I ask you to then create a contingency table there.
I wasn't sure because you was on with the night, so.
Yeah, so I think I mentioned this early in the semester. Those Connect assignments are going to be way harder than the questions I give you on the exam. Right? Because you've got a lot more time. You have me as a resource, right? So on the exam, you have a lot less time. Can't really use me as a resource on the exam. And so the questions will be a little bit easier. All right, those Connect questions will definitely push you a little bit further. So number 6, what's the probability an individual wants marijuana legalized given that they are Republican? So here's something we can't directly get from the table. Anytime you see this word given, what should you be thinking about? Yeah, see, straight line, right? We're thinking about conditional probabilities. So here, given that the individual is Republican, so I'll use this terminology as well. I get to the story problems and the Connect, sometimes it's a little bit more difficult. We've really got to think a little bit harder. Pretty kind on the exam where I'm going to say, given this, right? That's the term I'm going to use. Not, we know that the individual is Republican. I will use this word given, right? So it's very clear you can identify what that given is. Okay? Given that they're Republican, then what do you want to know the probability of? Well, whether or not they want marijuana legalized, we can write this as event LM. Once again, if you want to write R equals yes, legalize equals yes, you could do that. But once we have our 2 events, this is where we can go to our formula sheet. Oh, I should have, let's zoom in a little bit. There we go. Now, you'll notice this formula sheet kind of follows the organization of how we work through things. Population, sample mean, population, sample variance, standard deviations. That's the kind of first thing we talked about. Then we get down to here, weighted means, weighted variances, covariances. Then you go back up. Now we're talking about kind of probability loss. Okay. So here, I know that I'm looking for the intersection. So on this formula sheet, you'll notice it's kind of written 2 different ways. Right? And the reason why is because it doesn't matter if I say the probability of A and B or the probability of B and A. The ordering doesn't matter. Now, I'll probably be pretty kind of an exam. So I'll probably keep the ordering kind of nice like this first one where maybe just write down so you can match up to that formula. What's my event A? What's my event B? The conditional probability here, I'll move my cursor or I'll highlight this, is just the intersection. Oh, whatever, it's right here. The intersection of 2 events divided by what we condition on. So I'm looking at the intersection of my 2 events. And I'm dividing by the probability of whatever I'm conditioning on. Like I said, you'll have this formula sheet, you'll have that multiplication rule right in front of you. You should be able to solve for this. Okay. So I go back to my contingency table. Let's see if I can, which one was it? Was it this guy right here? Yeah. So what's the probability that they're Republican and want marijuana legalized? Scared. What's the probability? Yeah, right. What's the probability they are Republican and want marijuana legalized? 0.15. Okay. Are we clear on that? Or we're just shy. Okay. So 0.15 divided by what's the probability that they're Republican? Someone said it. It's hard to mess this one up because I gave you that the population was evenly split between Republican and Democrat. So we've got 0.5 down here. Okay. So I think this is what, 0.3. Okay. So I'll ask you, I guarantee you I'll ask you for a conditional probability using this contingency table. Now, one problem that's not on there that I might ask you is, let's say, what's the probability that they're not Republican or they don't want marijuana legalized, right? So I'm looking at now the union of two events. Well, here, hopefully we can kind of remember this. If not, we have a formula that if we want the union of two events, we can rewrite that as add the probability up of each event and then subtract what we're double counting, right? Subtract with that intersection. So here, once again, if it helps, write this down on your scrap paper or write it down in the exam. I don't care if you write it in the exam. The probability of our event A is that they don't want marijuana legalized. Our event B is that they aren't Republican. And then the intersection of those two, right? They're not Republican and they don't want marijuana legalized. You don't have to write this out every single time if you don't want to. I'm just doing this to kind of help kind of see what it would be if we did, right? But all I'm doing is following the general form of this equation. Okay? Now from here, this should be hopefully pretty easy, right? Because when I go to that contingency table, what's the probability they don't want marijuana legalized? We'll get through more of these if you guys kind of participate. 0.45, right? Probably they don't want marijuana legalized. I'm getting a little scared here. What's the probability they aren't Republican? 0.5, there we go. And then what's the intersection of those two things? Yeah, right, they meet right here. Okay. So now just a little bit of math. This is what? 0.85 or no, yeah, 0.85. So even though it's not on this practice exam, I very well could ask you to find a union. I wrote the exam, so take that for what it is, right? Probably showing it to you for a reason. So the only other thing that we can kind of check using these contingency tables, and we'll kind of look at the base in an example, is whether or not events are mutually exclusive or whether or not they're independent. So here, you do have to check to see whether or not this is true. So the easier one we'll do first, which is not, right? What has to be true if events are mutually exclusive? They can't happen at the same time. So that means that the probability I see A and B happen at the same time would be 0. The only way you should ever say yes to this question is if you look up in that contingency table and one of those top 4 left cells is a 0. I'm not saying that that won't be the case, but it's not a very interesting example. I doubt that that's going to be the case when you do it. So right away, thinking whether or not these are mutually exclusive, it'd probably be that no, they're not, right? They do have some positive intersection, right? The only way they're mutually exclusive is if that intersection is equal to 0. So we look up there, none of the intersections are 0. We can go to the exact events here, wanting marijuana legalized and Republican, we see that intersection is not 0. So no, they're not mutually exclusive. And then from there, it's kind of remembering our set notation, this upside down U, right? The U represents the union, upside down U represents the intersection or the and. So A is your answer, right? The intersection of these two events is not 0, so no, they can't be mutually exclusive. If you did see a 0 up there when you go to the contingency table, well, then the answer has to be yes, because the intersection is equal to 0. That's not even an option. Right away, these don't even make sense, right? If they were mutually exclusive, then the intersection should be equal to 0. So C doesn't make any sense at all. If they were mutually exclusive, the union doesn't have to be equal to 0. It's just the intersection. So C and D we could have ruled out right away. And then looking at D, once again, it's talking about unions. The union doesn't tell us anything about, well, the union being equal to 0 or not tells us nothing about whether these are mutually exclusive events. So here, really the only answer that makes any sense at all there, even if you didn't look at the table, right? Any questions? Does that make sense? Any questions on that one? So the harder one to check is for independence, right? And you're going to have to, I guess, kind of remember, well, you can do it 2 ways. I'll show you both ways. I'll show you the hard way first, and I think the easier way second. Okay. So I've got what? Being Republican and wanting marijuana legalized. So So the definition of independence is if that unconditional probability of an event is the same as the probability of that event when we condition on our other event. So if the probability that someone wants marijuana legalized is the same as the probability they want marijuana legalized given they're Republican, we'd say these are independent events, right? If they're not the same, we would say they're dependent or not independent events. Okay. Well, we have to check this. Now, maybe we solved for this in an earlier problem, right? I think that we actually did here. If you go up to 6, isn't that what we found? Right? What's the probability that someone wants marijuana legalized given they're Republican? So sometimes I'll be nice like that. Now, if you weren't confident in your other answer, you could solve this again. How do I find a conditional probability? This is my event A and B. When I go to that formula sheet, said the conditional probability is the intersection divided by what we condition on. So I can think about here. I want to find what this value is. I can find these two things from my table. Pretty easy to find the probability someone wants marijuana legalized from the table. Shut the door. I don't know what's going on. So the probability they want marijuana legalized would be what here? Yes, they want marijuana legalized. Go over 0.55. I think when we saw this earlier, didn't you say it was like 0.3 or something for that? And we can actually plug the values in again, right? So the probability they want marijuana legalized and the Republican is 0.15 divided by the probability they are Republican. So 0.15 over 0.5 is 0.3. That is not the same as 0.55. So we'd say that they are not independent events. The only way they're independent is if that equality holds. Okay. Any questions on that? Yeah.
There's always A, like it would, if it's independent, it would be equals A.
I mean this.
Yeah.
Yeah, right. So you need whatever's on the, I guess here's another way it's technical, not the most technical way to remember it, but you're looking to see whether or not the conditional probability, so whatever's on the left-hand side of this line should be the same as the unconditional probability you're looking at. So your event that's over here on the right-hand side that's not conditional should be the same as the first event you write or what's on the left-hand side of the line. Remember, this is what you're given to be true. This is still what you're looking for the probability of. So in both cases, you're looking for the probability that they want marijuana legalized. It's just that in the second case, you've got some additional information, right? You've got this given. Okay. So if we're going down here, this would be that no, they're not independent, right? We found these two things aren't the same. So no, they're not independent events. And then from there, one kind of way to check is, well, if I'm looking at completely different events, that doesn't tell me anything about events, right? Here I'm looking at the probability of being one marijuana legalized and the probability of being a Republican. I need to match up those events that I'm looking for the conditional probability of being Republican and comparing that to the unconditional probability of being Republican. Yeah.
Does it matter that what we found was LN R instead of R?
Yeah, so I've got this written two ways, right? We said that if A is independent from B, B is independent from A. So you could check this way, right? And notice that's not kind of what the answer is in the sense of you could have, it would have been better if you had the foresight to check this instead. So maybe looking at the answers might help you kind of know which one of these should I find. Now it doesn't matter because if I found that these are independent, right? Then I know, I found that these aren't independent. So I know the answer is no. And then just because I check to see if the unconditional and conditional probability of LM are the same, well, if they're not the same, then the conditional and unconditional probability are. So this is written using R given LM instead. But once I check for independence, I know that that's going to have to be the case for the other event as well. Now, personally, I think it's, I'll generally give you the responses like this because this is the literal definition of independence. So, if we look at this right away, I would look to see which ones can we rule out based off if we're not comparing the same conditional and conditional probability. We kind of already talked about, well, this one I could rule out right away. And then if I did the check and I know they're not independent, I know the answer is B right away. Now, this one doesn't make any sense because why? If they were independent, yes, they're independent. The conditional and unconditional probably have to be equal to each other. I could rule this one out right away. Now, this is a possible answer before I check to see if it was true, right? To see if these were equal. But we saw they're not equal. So then once we checked it, we could rule it out. But before we even started plugging numbers in here, you think about the only answers that really make sense here for B and B. You could rule out A and C right away. So when you're working on these multiple choice questions, I would look at the responses first, think about what you're trying to find or what you're trying to calculate, and rule answers out right away. Now, it's not the case up here. I didn't give you anything over 1, but for instance, if I'm asking for a probability and one of the answers is 1.2 or negative 0.3, hopefully you can cross those out right away, right? We know the probability has to be somewhere between 0 and 1. So sometimes I'll be kind of friendly like that. Even if it's a problem that's kind of difficult, you can kind of at least rule some of them out and take a slightly more educated guess, okay? Even if you're not sure where to begin. Now, there's one other way to check for independence, and it's on our formula sheet. I think it's a little bit easier. However, the responses are always going to be the actual definition of independence. We said that if events are independent, I could simply check to see if the intersection is just the product of the probability of both events. Now, I think, here we're dividing things, you're having to rewrite out that conditional probability. So maybe it's easier to check it this way. So here, if I'm looking for the intersection of my two events, and I want to check to see, is that the same as probability of both? So we looked up the intersection earlier, that was 0.15. Probability of LM was 0.55, and then I think the probability of the Republican was 0.5. Sure enough, these aren't the same, so that's a nice check to tell us that they're not independent, right? But it's not going to match up with the actual definition of independence. So in some ways, it's easier to calculate, but it's not easier in the sense that it's not going to match up to that actual definition of independence. Does that make sense when I'm getting it there? So whatever way makes the most sense to you, check independence that way. Any other questions on those? So that's about the extent of questions I could ask you, right? Added one in there, added that union question in there. So that might be a good thing to know how to kind of reproduce. After tonight, at 12, actually, as long as everyone's feeling hopefully okay with the Excel, hopefully they'll have it turned in by midnight tonight. Make sure you get your submissions correctly, because I will kind of release that answer key so you can start taking a look at that tomorrow. That has some additional questions, kind of like the ones we just worked through, right? The Excel portion of it, building the contingency table, that's Excel. That's, we don't have to worry about that necessarily for the exam, but the questions that follow to then use those probabilities that you calculated, you could see very similar questions on the exam that look like those. Okay, so just more practice problems for you to look at. Okay. All right. We'll skip this one because I think for the sake of time, I want to try to get to some I think are a little bit more difficult. Okay. I think maybe this one's a little bit easier. I'll show you a harder one that I wouldn't ask you to do this example. So we'll switch over to practice exam A. I probably wouldn't ask you to do this one on the exam. I'll try to make it so that whatever the events or the states of nature are and the outcomes of the test kind of have different terminology, so it's not easy to kind of confuse them. This is an example where if you're working through this, it might be easy to kind of confuse that. Because we're looking at a lie detector. So there, the state of nature is I'm either lying or I'm not. And then the outcome of the test is whether or not the lie detector says I'm lying. So those terms are kind of the same. So I'd probably give you one like the other one where are you using or not using steroids, and then do you get a positive or negative test result for steroids, right? There, those are two different words. So when you're writing this out, it should make it a little bit easier. But I'll work through this harder one with you. And hopefully I'll kind of give you some, I guess, a way to, even if they were the same, kind of help keep these things kind of organized in our mind. So generally, you'll see something like this, where I've got 3 questions that are related to this information I'm given. Some of this I might have to use Bayes' theorem for, some of it I might not have. Okay. So what I would start out doing, if it was me on the exam, is write down everything that this information gives me, because I need that for the next 3 problems, right? And just kind of help organize it here. So suppose that given that someone is lying, the probability a lie detector test shows they're lying is 90%. So given, this is where I'm so bad at English. Is this line? I probably, is it Y? That's what I thought. I probably did it wrong on the answer key. I did this wrong one time and like no one told me, and they made fun of me at the end of class. And I was like, I can never remember which way it is. I rely way too much on autocorrect. So here's my state of nature, right? But they're actually lying. And that's what I'm told given. Once again, I'm using this terminology of given. I know on some of those Connect assignment problems, they don't use that terminology. It's a little bit hard to figure out exactly what you were given. When it comes to the exam, it's pretty easy. And then what I would do to kind of differentiate between your outcomes of your experiment and your states of nature is think about this as, well, what's the probability that the lie detector test shows that person's lying? So whatever your test is, I would write like LD is equal to this, right? The test is equal to that. When I had like the, whether or not the test was positive, right? If you always write it out that way, it's a little bit easier to remember wherever my equal sign is in my event. Those are my outcomes of the test, right? And then here's just kind of my underlying state of nature. Okay. Notice it's the same word. So if I were to just start writing this out without doing this, this problem becomes kind of tough, right? So I just think always using some type of identification for the test is equal to whatever the outcome of the test you see is. Okay. So this is 0.9. I'm then told what? Given that the individual is not lying. So you could do this two ways. You could write not lying, or I guess if it's easier, you could write telling the truth. Whatever kind of term connects better with you. The probability the lie detector test incorrectly shows they're lying is 20%. Okay. And then the last thing we're told is recent studies show that on average, people are lying about 5% of the things they say. Okay. So there we don't have any conditional probability, just the underlying probability that someone's lying. Okay. Now we could start to tackle these problems, and we may not need to know. I think on this price exam, I can't remember which one is which now. You may not need to know some other probabilities, but from these three, so you'll always kind of be given three, you should always be able to then know three other probabilities. So the easiest one, and you could draw this out as a tree, or if you write these down like I have here, you know that each one should have a counterpart. Okay. So here, what's the probability? If I know the probability that someone's lying, what's the probability that they're not lying? Yeah, right. There's only two states of nature. I'm either lying about something or I'm not. So I know those have to add up to 1. We then had this idea that, okay, given that someone is lying, if I know that 90% of the time the lie detector picks that up, what percent of the time will the lie detector incorrectly not pick that up, right? Show that they're not lying. Well, given that I am lying about something, the lie detector either says I'm lying or it says I'm not. So if I'm conditioning on the same state of nature, these probabilities should add up to 1. Right? And that's why if you write them down and kind of write them next to it, you can always remember, well, the conditional probabilities that I'm not directly given, but that I can find, right? I'm just going to use the same given, right? I'm conditioning on the same state of nature, but then I'm just going to look for the other outcome of the test. And now I kind of know that my rows that I've written them down add up to 1. Now, if the tree makes more sense, so you can do it that way. I don't know. I think this is kind of a nice, easy way to do it as well. Now we've got everything we could ever need to answer some of these questions. Okay. So it might have been a little bit overkill for some of these, but hopefully we'll use a lot of this. So the first thing is, what's the probability a person is lying and the test says they're telling the truth? So what's the probability that someone is lying? And here, I wasn't writing down truth. So if someone's telling the truth, we could think about, just to kind of keep this consistent, we'll say that they're not lying. All right, it's the same thing. That's just, we're kind of using a different term. On the exam, I'll make sure I kind of use the consistent terms. Like these are probably a little bit harder than what you would see. So if I'm looking for the intersection of two events, I can rewrite that as a conditional probability times what I'm conditioning on, right? That's kind of multiplication rule, just rearranged. Good question.
Not really, it was just not lying, shouldn't that be LP, it's not lying?
You're right. That was the lie detector, wasn't it? So you can see we have kind of the same outcomes on the test as the state of nature. It does kind of come a little bit confusing. That's why it is a good practice to kind of write in that test is equal to whatever the outcome is. So I got the intersection of these two. I can rewrite it as the conditional probability times what I'm conditioning on. So here is my event A. Here's my event B. So my conditional probability I want is B given A. So B given A times the probability of what I'm conditioning on. What am I conditioning on here? The probability that they're lying. Right? Now, hopefully, if I have everything written down, this is pretty easy. I plug in what? 0.05 down here. And then this, well, this is a good example where I wasn't directly given this probability, right? So if I hadn't have done this before, I would look at the three things I was given and say, well, I don't have this probability. This can't be a question I answer. Well, no, if you're given those original three probabilities, we automatically know they're three counterparts. So because we already had that work done ahead of time, we could just plug in a 0.1 there. Any questions on that idea? So sometimes you'll have to find these missing parts, right? And if you just do it all when you first start tackling that problem, it might make it a little bit easier. So this is like the same thing. I won't necessarily waste time on 11 just for the sake of time. But I think the only thing that changes here is the underlying state of nature. So you could kind of work this out. You're just writing this out, and you have slightly different values, right? But it's the same setup. You're still looking for an intersection. It's just that I changed what the state of nature you were looking for was. Okay. What might be harder is once you get down to one like 12. Is if you're asked for a conditional probability. So this is where I wish I had more board space. But does everybody have this written down? Can I erase this? Otherwise, I'm going to be like crouching and trying to write. It's not going to be pretty. So here we've got, given that an individual fails the lie detector test. So given that the lie detector test shows they're not lying, what's the probability that the person is actually telling the truth? Or what's the fails the lie detector, which would mean, sorry, lie detector test shows they are lying, right? I kind of even wrote that here, right? The detector determines that they lie. What's the probability the person's actually telling the truth or that they're not lying? So at this point, if you're asked for a conditional probability, the flow of the exam is going to be similar to the practice exam. So, earlier when I asked you for conditional probability, you have a contingency table, you can probably just use that multiplication table. If you try to write out the multiplication rule here, you'll be dividing by the probability of what you condition on, which would be that the lie detector test shows lying. You don't have that probability. You've got a bunch of conditional probabilities, but you don't have just the underlying probability that if I have no other information, that I get the response in the lie detector that someone's lying. So even if I tried to write this out, right, as a conditional probability, or use my multiplication rule, I'll figure out why I don't have those probabilities. So that's probably going to be a good indicator. Also, the point at which it's at on the exam and on the practice exams. I probably have to use Bayes' theorem here. Right? So like I said, I could write this out like I had the multiplication earlier. I'll be dividing by something that I don't have the probability of. Well, what can I do? I can break that down. We had all those equations that we subbed in to get Bayes' theorem or Bayes' equation. Now we can think about, here's my S, here's my E. Now it's just a matter of, I've got this formula in front of me, write this out in the context of my example. Okay? So the probability of S would be what? That they're not lying. Times the probability of E, which is that the lie detector test shows they're lying, given S, So if they're not lying. Divide that by, now here's to save some time. And you could, doesn't, have to remember this, but the first part of the numerator is always, sorry, the first part of the denominator is always the same as the numerator. Right? This was the idea that the numerator represents the number of people who were not lying, but the lie detector test incorrectly showed they were, right? Like our false positives. Out of all the people that got result where the lie detector test showed they're lying. So that would be composed of people who the lie detector test shows they're lying and they weren't, plus the other state of nature, the people that were lying, right? Or S complement times the probability that the lie detector test showed they're lying. And I'm going to run out of room here, but given that S complement, okay? And then I could write this all out again, but it's the exact same thing as what I had above, right? Yeah.
So how do you know when to use?
So a non-technical way I already said. So what did I just say about the flow of these exams? You'll be asked for a conditional probability up here with a contingency table. That means you can probably use the multiplication rule. You then get down a little bit further and you've got kind of conditional probabilities you're given, and then you're asked for another conditional probability. This is probably going to be a good, once you get to this point, you're probably gonna have to use Bayes' theorem. Now, technically, like that's not a technical answer. Before I'm going to erase these real quick, and I'll kind of show you. So, and hopefully once you have this written out, it would just be a matter of plugging in your probabilities there. I'll show you the answer in just a second, kind of what that would look like. But let's say now that I have everything written down, hopefully you have it written in front of you. If I try to use this multiplication rule where I find a conditional probability is the same as the intersection of the two events divided by whatever I'm conditioning on. If I go back to those 6 original probabilities that I have, did I have either one of those things? So no one write them down in front of you, right? We were given 2 conditional probabilities for which we knew 2 other conditional probabilities. I was then told the probability that you're either lying or you're not, and then I knew you probably you're not lying. I was told nothing about just the underlying probability that the lie detector test comes back that's saying that you're lying, and I was given no intersections, right? So I guess a technical way to be would if I have this conditional probability I'm looking for, I write out the definition of the multiplication rule, and I don't have these probabilities. Well, that tells me I'm going to have to do all that substitution to get down to Bayes' theorem so that I can use the information that I was actually given. So that would be kind of the technical kind of way that you're going to, in practice, like outside the exam, you're doing it. Like I said, I keep the flow of the exam kind of similar to how we covered things. So, if you're looking at these practice exams, you'll notice you're usually finding a conditional probability earlier on where you can use the multiplication rule. And the next time you're asked for a conditional probability, it's likely going to be that you have to use Bayes' theorem. But if you try to, you'd figure that out hopefully quickly that I don't have these probabilities. I need to do something else. Does that make sense or answer the question?
Yeah.
Okay. Any other questions on this? Because I didn't write everything completely out, but and I didn't kind of plug all the values in, but just for the sake of kind of getting through some more examples here. Does that help? All right, got 12 minutes. So what do I want to do? I want to. So here we've got some binomial stuff. You've got some uniform. Where's practice exam A? Let me make sure if there's nothing on there, then I'll kind of give you some additional ones. I think. Oh. Yeah, so kind of identifying the difference between the binomial and the Poisson. So I use an example in class. But one thing I might expect you to do is kind of what we covered at the very end of last class or beginning of last class. I mean, it might have been I think so, where we're converting time intervals, right? So I would go back and look at those examples that we did in class as kind of a refresher of when I want to use these Poisson distribution examples where I'm given maybe some average number of successes over a longer time period, like a year. How do I then convert that into the average rate for a smaller time period, like a month? We said we divide by some factor, we divide it by 12. Now that I have that new average or that new lambda, now it simply becomes go to that Poisson distribution, which I've got right here. Now I've got my new lambda for the time interval I'm interested in. E is just that value that hopefully we found in our calculator, not 2.7128. For whatever reason you can't find it. Hopefully you'll have found it going into the exam Friday. If not, I'm going to ask me where it's at in your calculator. But I'll remind you of what that value is just in case you don't remember on Friday. So that's just the value, and then X is just going to be, well, what's the probability that I find 2 successes or 4 successes or whatever number of successes the problem defines. So if I'm looking here, what's the probability that less than 2 people? Well, okay, it's a little bit trickier because if I want the probability that less than 2 people were struck by lightning, I've got multiple numbers of successes that fit this criteria. Yeah.
Did you say lambda is 3?
Yeah, so I would have to be given lambda here. Yeah, that's 3. Now, if I wanted a problem where I was then looking at the number of people struck in the next month, I would have to convert that lambda to whatever the average rate would be over a month. So there's 3 over a year. In any given month, it would be 3 divided by 12. And that would be the new lambda value that I use. It doesn't apply to this problem specifically, but I would go back to those ones that we worked on in class to kind of just show, to get my new lambda, it's just a matter of dividing by some factor. And I'll keep it real easy. Days to week or week to day, month to year, or year to month kind of things that we would know. And I'll probably be obnoxious to say there's 12 months in a year, 7 days in a week. So here, if I'm using that Poisson distribution, I could ask you to find the probability of exactly 1 number of successes, which makes it easy. You just go to that formula, you've got your lambda of 3, you've got your X value, whatever it is, you plug them in, you're good. But if I want a range, I have to find the probability of every single possible number of successes that meet this criteria, right? Or that are in that range. So here that would be what? Yeah, we're dealing with these discrete random variables. The only continuous variable we had was that uniform, which will be kind of notated to us, right? That it's uniformly distributed and told to us that it's uniformly distributed. So we're dealing with a discrete random variable. The only number of successes we could see are 0 and 1. We then have to go use that Poisson distribution equation once, plugging X is equal to 0, lambda was 3, write that number down. We then use that Poisson distribution equation again. Lambda is 3, X is 1, write that number down, then add them up, right? So if we want, kind of see what that looks like. All right, so lambda was 3 to the X, e to the negative lambda over X factorial, lambda to the X, e to the negative lambda over X factorial. Now, a lot of stuff becomes easy in these questions, right? 1 and 0 factorial involve 1. Anything to the 0 power is 1. So this would hopefully be something that's a little bit easier to calculate. Now, if I'd asked you instead something like, what's the probability you see 1 lightning strike next month? Well, that was the idea where, okay, if I know that there's on average 3 every year, the average rate over a month would be what? Just 3 divided by 12. Yep, so there we would have lambda as 0.25 to the X, e to the negative lambda over X factorial. Right? So it's simple as that. There's just one added step, which is you first have to find what your new lambda is. Does that make sense? Okay with that? So what if instead we use this binomial distribution? Okay, so I think there's a couple questions on here. Go to practice exam A. This one I've got what? Percent of people that have a visual impairment. Now, if I'm asking you, hopefully if I ask you a question like 17 on the exam, this should be insanely easy, right? So if I've got that 64% of people have a visual impairment and I select 15 people at random, what's the expected number of individuals that have a visual impairment? So one thing we said with these random variables is our mean. Another word is the expected value, right? It's kind of the most likely outcome. So the formula sheet reminds you of this, but it's kind of this intuitive. You just take the number of trials and you multiply by the underlying probability of success. So our number of trials here was that we were looking at what, 15 people. So we had 15 people, the probability that if I selected one person at random, they needed corrective lenses was 0.64. It's a matter of just 15 times 0.64. It's gonna be what, like 8 something? Wait, 9 something? Yeah, 9.6. There we go. So this should be like easy points. All right, you've got that formula on there. Hopefully remember, like once we know we're dealing with this kind of binomial distribution. And the way that we differentiate the two is here with the lightning strike example. How many people can be struck every year? I don't know, I guess technically the number of people in the population, right? But it's really open-ended. Anytime we see that we have a cap on the number of successes here, what's the highest number of people I could see have a visual impairment? All 15 out of 15, right? I've got a cap on it. That lets me know I'm using a binomial distribution. If it's kind of open-ended, I've just got this time interval. Well, that's situations where we're going to use this on. Okay. So hopefully 18, just kind of for the sake of time, you know, there we've got N, we've got P. I want the probability that exactly 10 out of the 15 have visual impairments. I've got X is equal to 10. It's just a matter of plugging those values into, and this is where just practice going back, plugging those values in that binomial distribution equation, trying to reproduce some of the answers that we saw on the slides. If you want to go back on some of the homework assignments, maybe even the ones on the Excel, try to reproduce them by hand. Make sure that you can get that entered into your calculator correctly. Like I said, something that might make it easier, kind of break it down into parts instead of entering it into your calculator all at one time. It's easy to make parentheses mistakes. Okay. But what might be a little bit trickier is I think the next question said, what's the probability that, what was it? At least, right? Or probably that less than 14 people have a visual impairment. So if I follow the train of thought I had earlier, this is going to be equal to what? The probability that 13 out of 15 plus the probability that 12 out of 15 all the way down to 0. Do you think I expect you to do that in a 50-minute exam? Probably not. So how can I solve for this instead? Yeah.
Probability of 14.
Yeah, if I think about this as my event A, well, I know I can find the probability of A if I take 1 minus the probability of its complement. Well, what's the complement of being less than 14? Greater than or equal to 14. The only probabilities that fit this criteria would be X is equal to 14, and then add to that the probability X is equal to 15. Now I only have to use that binomial distribution equation twice, right? Shouldn't take me quite as long. Also, when I'm looking at all of the trials or successes, this was a situation where once I start plugging in N and X to be 15, things start to become 0, and I start to be able to kind of, 0 factorial is 1, anything to the 0 power is 1, and things become a lot easier, right? So I would write these out, and before you go to your calculator, try to do as much of the math you can in your head. The N minus X, hopefully we can do it. I'm not choosing crazy numbers, so you can probably do that math in your head. 1 minus P, 1 minus 0.64, write that number down, as opposed to like keeping all these parentheses along the way. Okay. Any questions? So we're running out of time a little bit here. So this is what I would say. As you're studying, those practice exams are going to be really good examples of the kind of questions you could see on the exam. The thing that I would add in there that's not on there, I showed you how to find unions today. That's a big one. Kind of knowing how to use that Poisson distribution, changing the time interval. That's something that doesn't pop up on either one of those exams. That would be a good thing to know how to do. And then one thing we didn't cover today, but obviously we should know how to do if we go down here. kind of review what we talked about with that uniform distribution. I don't think that one's too tough, especially if we draw out that visual. We're really just finding the area of rectangles there. And then I think another tricky thing might be that I saw some people kind of write down. And I think going back to the slides and looking at the income data, it's kind of a reminder how to do this. But weighted means and weighted variances. Now, some type of problems that you could see related to that as well is just regular discrete random variables. Well, there you're still using the process of a weighted mean and a weighted variance, but we said our weights or probabilities, well, then some of our weights will always be 1. So it actually became a little bit easier. But reviewing how to solve for those weighted means, weighted variances will kind of help you with those discrete random variable problems as well. I likely will only ask you to find a weighted mean, but I could ask you to find the variance of a discrete random variable. Right? So if you're not as comfortable with a weighted variance, I would say might be okay. Know how to do a weighted mean, but know how to calculate the mean and variance of a discrete random variable. Should be a little bit easier. Our denominators become 0 there, right? The sum of the probabilities or the sum of our weights would be 1. Okay. So like I said, 17 to 18 multiple choice questions, a couple short answers at the end. Definitely some of the short answers might be a little more related to kind of some of the later stuff that we've done in the semester. Allows me to give some partial credits just in case that binomial per sign you did enter into your calculator wrong. I know that's a little bit tougher, so that's probably going to be the one where I want to be able to give more partial credits. Okay, so I would expect short answer to be some of the later stuff, the earlier stuff kind of being multiple choice. Okay, I'll bring the formula sheets. I'll have extra sheets of paper. I'll try to get here a little bit early, so if we want to get a slight early start on it, that way we've got a little bit more time. Other than that, any questions for me before you guys get out of here? Okay. So make sure you get that Connect Excel tournament ended today. Also, when I reset the due date, some of you already contacted me. If you didn't have it done, it automatically submitted it. So you want to finish that up, just do the problems that you didn't do, and I'll go back and manually and add those points together once that due date is passed. Okay. All right. I'll see you guys on Friday.